3, 2, 1. Hello everyone, it's July 13th. So yesterday spent a lot of time trying to write async IO to improve the performance of that app, of that data pipeline app. It turns out it didn't work. I think the reason it didn't work is because I only optimized one part of the pipeline, which is write into Elasticsearch. But during those writing functions, there are also other calls to Postgres, to Cassandra, and to Kafka. And none of those have been optimized to async IO. And it's not impossible to change those parts into async, but it's going to be a huge undertaking, and it doesn't really align. It is not aligned with what we are moving forward towards. So that's it for async IO for that. And it's still a good learning experience about async IO, but it's just not something we want to do at the moment. I think we want to more focused right now, not even on parallel processing right now. We want to focus on batching. So instead of handling the parallelism ourselves, we try to batch it and send it to ES. I'm going to let ES handle everything. And for us, all we need to do is just to batch. So we're going to put a lot of the documents that right now we are inserting to ES individually. And we think we're opening too many write operations to ES, and it's kind of hogging up the resources. So we can put them together and then do one write. Or it could be a streaming write. That doesn't really matter. We don't really care. We just need to put them together and do a bulk. Put them together, do a bulk. And we'll see if that can improve our throughput. Currently, the throughput we reach as low as like 24, 25 operations per second, and that's low. We want to be consistently at 60 to 70 per second, and if we can do that with about 24, 25 pods running on Kubernetes, so that's what we want to reach. So basically, we need to improve the current throughput by 3 times, which my manager thinks it's definitely doable, and we'll see. All right, so today we're gonna handle the binary tree first. I've seen this before, and then we're gonna do this problem has been stuck for like 4 or 5 days. You're very welcome. All right, so we're gonna construct a binary tree from pre-order and in-order traversal. Yeah, I've done this before. I remember the method I used was stupid, and there's a smarter way to do this, and I don't remember what that smarter way is. Okay, pre-order is 3, 9, 20, so root, left, right. And in order is left, root, right. And given this, we want to rebuild the tree. How do we do this? So, man, I feel like I'm going to fall back to what I did last time. So, pre-order always go root. So when we go root, so we know the root is 3, and then we can, now we're going to say to divide, but we don't know where to divide. We just know 3 is root, right? And that's all we know. So we'll be left, root, right. I remember there's a divide in this thing. Unique values, each value, I don't remember. I remember it's going to be a very smart way. Root, left, and right. So we find a root, then we can split this into two parts, because this is left, root, right. So we know the root is 3, so we go inside here to find where it is, and it's 3,000. We can turn that into a hash map. So we have values because they're all unique. So we have values and their index. So 3, so we find the index. Index is 1. So we know from everything to this is going to be on the left. Everything is going to be on the right. So we can build 3 and we go left. So we handle this part, right? And then we know we have a left, so the next one is going to be the left. So the root is going to be 9. So we find that root is 9, and we keep dividing, right? Because this one is this left, so we always go to the root, right? We always go to the root until we basically go to the most left, so we have nowhere to go, and the next one is going to be, so what's the next one going to be? Oh, it's going to be on here, because we divide left subtree or right subtree, and then the left subtree going to start from here, right? And then we can consume. Every time we consume, we're going to go more and more and more. And then once we're done, so this we can just keep going, right? So we go left, root, root, and then we have nothing. And then we're going to go right. So the next one, once we hit everything, then this one is going to be on the right. And how do we handle that? So that we just go look for we create nodes. We create nodes following this. So 3 points into a node, 9 points into a node. So when we do 3, that's the root. And then we next do 9. We find 9. Well, I mean, we shall split, right? We shall split to the left half and the right half. So on the left half, so we'll always return the root. So we're going to go left, right? And on the left we have a range. And then inside this range, we're going to see the next one. If the next one is in this range, so that is going to be the root. Then we keep dividing. And eventually we return that, and that's going to be the left. We can try. I want to try this. That seems to be different from how I was trying to do it last time. Because I kind of remember the last time when I hit this problem. It was very bad. I have to use a lot of hack to kind of get it to work, which I don't like at all. But this time, I hope it'll make sense. And of course, we're not going to test this. We're just going to run it. Okay, so build tree, pre-order in order. So what we want to do is Like what do we want to create? Because I also want the indices, right? So if the current one is not in my index, so the next one, if it's not in my index on this, then we have to go on the other side. And this one has to keep moving forward. So I need indices, so I know where which part I'm dealing with. Okay, so I can say def build. Okay, I need my range. So I have a low and a high. Okay, I have a low and a high, and I want to return a tree node. Well, technically an optional tree node. So given low and high, that's what I'm going to return. But before we're doing that, we need to build something. When I say nodes equal to for I, v in enumerate in order, right? When I enumerate in order, and we're going to create a tree node of value is v, and we have I and this, right? And we're going to do v and this, so that's going to be a dictionary. So nodes dict. So by v, we can query this. That's what I want. So now we have a low and a high, right? And we need an index. Index is the pre-order index. Now we're going to say the current val is going to be pre-order index, and shall say n equal to len pre-order, and we say if index is equal to n, return none. Okay, now we have the val. Then we need to get the index, current. So current index and node equal to nodes dict val, right? Actually, I don't think we need to use val again. I can just do this. So we get the node, right? So that's the root. And what we're looking at right now is the root. And then we're gonna call build, gonna be low, and current index minus 1, and index plus 1. That's actually not. I want a global index. Really, a global index? Yeah, how do we handle the index? So we keep moving, and then we go to the right. It won't be index plus 1 right here, because every time we do this, index will be incremented. So we need to return the index. So we need to return two things now then. So like we'll know what the next index to call. So return this and an int, right? Yeah, because for the pre-order, we're just gonna go this, and then this. kind of build up the entire left, and then we move on to the right. So the build, I'm going to return a new index. So current index is for the pre-order, in-order index. So I should be II, let's call it II, in-order index. Right, in-order index, this is what I'm looking at. And then current index -1. Yes, load to this with II plus 1. Because I'm used up II, so I need to go to the next one. But this one I can return to the new II, right? And we say that's going to be a left node equal this. And a right node, new II, shall equal to build current index +1 all the way to high, and we say new II. So what is this new II? New in-order index is the one that whatever has been consumed. So we return the one that after I finish building my tree. Yes, it's rightmost, right? Rightmost. So dash up +1. And then we're going to return. Oh, and then we're going to do, I say node dot left equals this. Node dot right equals this. And I return node and NII. That's the most front. But then this one we have to change. And then we return II, because we have to return the current, the most. And then we can call build 0 to high is n-1, right? And II is 0. So we shall return this. Okay, let's see if this one works. I don't have too much confidence. List out of range. Pre-order. I didn't say II is in order. It's not pre-order. Man, I got confused myself. This II is pre-order, so that's PI. Yeah, that's PI. That's pre-order. My bad, that's pre-order. But why would it be out of range? Because I checked, right? If PI is equal to N, then we return. Return PI. And then it should be the pre-order index +1. I'll give us a new pre-order index. And I do a new pre-order index +1. And this will give us a new pre-order index. And I return a new pre-order index. Why would this be out of range? Debug. I need to debug this. Interesting. Let's print. Let's print PI. And then just kind of see how it progress. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4. Okay, we are very wrong here. All right, let's see. So we call 0 to 1, 2, 3, 4, 5 to 4, right? 0 to 4, and then pi is 0. So we say 3, right? So we have a current index, and then, oh, we forgot to do a check. I know. We forgot to do a check. And of course, this way I should say larger than equal to, but we forgot to do a check. Two things. So I have to first do a check, and then, so now pi, now we get the index, now we have to see, right? If current index is within what we prescribed, then we do all this. If it's not, if it's outside what we prescribe, so the current index is outside, that means that node is not there, then we shall just return none and whatever pi is this. Okay, try it again. Nope. Type. Huh? I'm returning a tuple? Oh, yeah, I am returning a tuple. That was wrong. I got 397. Which means I got 3, I got 9. And I didn't get to... I immediately got to the end. That's very interesting. What happened to 20 and 15? Okay, so 3 is correct. And current index shall be 0. And we're between 0 and 0. Right? So pi is this, and the pi is here. So 9. So now we got a 0, so that's good. And then I will build smaller. There's an issue here. But anyway, current index, I shouldn't say current index, I should just say this is an in-order index, right? So this is just in-order index. So the in-order index minus 1, in-order index right now is 0, so this becomes negative, right? And pi just plus 1. Now, because pi already plus 1, and we didn't do, so I think this pi shall be minus 1, because I didn't do. I shall stay where they are. Just stay where they are. Okay, let's try this. We shall stay where they are. Stay where they are. I like to use this one again. Okay, it will stay where they are, so we do a minus 1. come on, dummy. I see 15. I see 20. This one might be right. I forgot. This has to go. Yep, this one is correct. And let's use both. Okay, try this. Okay, so this one is pretty good. I believe we hit the right solution. I'm gonna just open this. Let's do all three of them. 105. So the ideal is we use pre-order as the order of progression, and use in order as the recursion structure. Each pre-order value is pre-order goes to the left branch first and then right. No, pre-order goes to the pre-order visits the root. Then we can find in order the position, the location of the root, and divide in order into two halves. We continue with pre-order and visit the left half of in order. Whenever the current node of pre-order, right, lands in a value that is outside the current range of in order, that means we have finished all the nodes on that side. We need to switch to the other side, to the right side, right? To the right side. The only tricky part is to keep track of the current progression on pre-order. We use the return value of recursion to do that for us. I think this is ON, that's why it's kind of fast. Right, let's see the methods in the past. 202. 203, we have one more. And we go a little bit faster. So this is the slower methods, which is the official solution. And if you think about it, we really don't have to store the tree node. We can build it like that. A tree node int, exactly as what we do. Now I return, and then root, yes. II is the in order index, and then root.left, ni equal to build this, root.right, ni equals this, and return root and this. Yeah, so I think it's the same idea. We got a root. Yeah, that's how we do the root. And it's the in-order index. Yes, now we split based on the in-order index. And we progress I plus 1. And I return the current one. And we pass ni, so we don't do the ni plus 1 here, so we can directly pass ni here. And this is the right half. We return this. Yeah, you're wasting. You're wasting. Directly do this and do this. Save us 2 lines. Now the difference is here I do a plus 1, and here I just use the same thing. So if it's not good, it will return the same thing. So that is going to be if I don't plus 1. So I have to plus 1 on here to say, okay, I want to go this one. But then I return, and when I do it again, I don't keep plus 1. So this always points into the next one, right? So if I return this, it will point into the next one. So I can always point it, and this one will point to the next one. Yeah, so I can remove this. And the only difference right now is this actually is fine. I can build a node here. It doesn't really matter. What matters is they only check this. J1 larger than J2. They did not check this. Maybe they don't have to. That's okay. What's this solution? No hash map. Build. Parent. Build ij. That's still the range. So I is pre-order. Okay. That's always a root. And then what is J? What does J stands for? Build left subtree ends when the in-order hits the current root. So I plus 1, let's just keep going. J is the in-order, right? I'm going to build that. And whenever it hits the parent, that's true because when we build the left tree, it shall never hit the parent. And then J is just incrementing slowly. And I'm going to build that. And we say whatever we hit is going to be the left tree. In order is this, J is this, and we have a new root, and then we keep going left, and keep going left, if the in order j is equal to parent. So parent starts from here, right? And then parent is here. Then if the left hits the parent, because it's split in two, right? So this is the parent value. So we go left. If we have no left, which is j, if we don't have any left, then j will meet the parent, and that's when we know that's it. Hold on. Building left subtree ends when the in order hits the current root. We hit the current root. This is the current root. So that's the parent going in for the left. Because on here we have a root, right? Then we go something, and the next was something, 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 then we hit the root. So we go one more on this will be like here. Wait, hold on, I got confused. We start with 3, right? I start with 3. But here, we're all the way to the most left. Right, and now we keep going on, running 9. But in that code, we'll keep pushing I plus 1, right? Because we keep pushing I plus 1, I plus 1. So j stays the same, right? J stays the same. And then pre-order in the root, so this one become root, this one become root, this one become root. Until at one of them, we push all the way to the first j equals 0. So when j equals 0, equal to the root, and that's it. That's the end of the push, right? And then what we'll try is like, okay, so root dot left is none, and then we try the root dot right. So root dot right, ni, is the same thing. And then we do ni plus 1. Now ni again, and then we do nj plus 1. And now we do parent. Pre-order I. Pass a parent, and then we pass and we create a root. How are these two the same? Apparently not. I still don't understand this code. J is in order, okay? So we go to root, and then we go left, I plus 1, we go left, I plus 1. Eventually, we will hit something. Preorder I, which is the root, and then we go left, and it's the same. So I say now we have gone all the way to the left. Now we're going to go to the right. And to go to the right, it's basically I plus 1 and j plus 1, which is just the next value. And the next value, because the parent, I'm passing this parent. So it's the parent of the root. So root is here. And the parent of the root. So if this one is equal to the parent of the root, then we also ends right there. I don't understand. We go all the way left, right? We go all the way to the left. So this is the parent. So I'm at here, and I know who my parent is. And then I pass on to my child, and it turns out it's the same as me. It turns out it's the same as me, so I am, and if this one plus 1 is equal to my parent, then that's it. So we build the left subtree, right? This is the root. And now we need to build the left subtree. And once we're done, we need to build a right subtree. The right subtree is this root is here. And want to build a right subtree, it has to be on the right side, right? It has to be on the right side. It's because, what is parent? Parent is from the preorder. The root, left, and the right. the root, and keep going, it's on the left, and keep going, it's going on the right, and maybe root, maybe left, left, left. So we hit the root, we hit left, hit the root, that's the left. And we go right, when we're done, we hit the parent. Yeah, okay, I see now. I see now. If we build a right subtree, we hit my parent. This it's my parent. We go left, blah, 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 blah. Everything on the left. Done, now we hit the parent, then hit right. I don't think I can figure out this one. Hash map it is. It's a bit easier for me to reason with. Okay. I'll just stay here. Okay, with a merge. I gave it a thought, so I'm trying to see if the new idea works. So we're going to use a dictionary, and we're going to actively handle this dictionary. And we need to use doesn't matter which one I use. I just want to pass. Intervals. It's a dictionary. Self.count. So this we just return self.count. So everything happens here. And I like to keep track of the max, right? We have math we do. And min, left. Just to reduce some of the operations. If right is smaller than self dot main left, right, then actually it would be good if not self dot intervals at the beginning. Okay, then self dot intervals left equals right, self dot max right equals right, self dot max main left equals left, and self dot count equals right minus left plus 1. That's initial. Else, if we have, then we need to check. If right is smaller than self dot main left, then self dot intervals left equals right, self dot main left equals right, now equals left, right, and self dot count plus equal to right minus left plus 1. Now if left is larger than self dot max right, self dot intervals right equals right. No, right equals left equals right. It doesn't change. Self dot max right equals right, and self dot count plus equal to right minus left plus 1. These are easy, right? and then else. Now we have an overlap. So what do we do when we have overlap? What we do is we're gonna have for the lefts equal to sorted, self-dot intervals, index equals bisect, right, left, and the current left. We get an index, which is in between, and if it's equal, we are taking on the right side, which is fine. Then we have the first say, right? Then we have situation is we have some left, let's call it L1 and L2, and our L is in between. Now if our L is equal to, because the way we set up, then we can check if it's equal to, it's equal to is the same thing, right? We're always going to check this and check this. So see, do I have a limit on this? 0 and 0. Okay, that's the smallest. So but a mean left, like a realistic mean left. I'm a really large one. Yeah, we can go, let's say, math.inf minus math.inf, like that. Now when I come in, if right is smaller, no, I don't like it. I like this. We can set this one at the beginning. So now we have to consider sticking out, right? If it's 0, that means it sticks out. If it's anything that's not 0, because if it's the same, we'll go to this one. It is fine. So we always go this one minus 1 and this one, so in between these two. Unless it sticks out. Well, it won't stick out on the right side because unless it's equal. No, it will stick out. It will. Because this is handle larger than max right. Let's consider every single situation. If index is equal to 0, okay, that means it sticks out on the left. So in that case, we need to see where the right ends. Oh, we might have to do, we have to do both. What do you mean? We have to do both. We cannot do both. Then we have to loop them one by one. Now we can. On the right side, see where they end. But we still need to go one by one. Because then we need to remove them. Okay, so then each one that was sticking out, so we're just gonna go from 0. We check the right and see if it's smaller, then I remove it. And then we go to the next one. Right? Then we go to the next one. And okay, for each one, we need to first check if this one is in, right? If the left is larger than the current right, then, and I assume I already handled everything, then we're done. Okay, then we're done. We add the current, then we're done. So if it's equal to 0, actually it doesn't really matter. It's a stick in between, right? So whichever index. Because we point in S1. And if they're equal, I guess we'll handle the case where they're equal. Otherwise, it's going to be in here. So we're going to start from this one. If they're equal, then which one do we start? We still start with this one, right? And no matter what, because I'm in between these. Oh, but I don't know. So I have to check the previous ones right. Damn. Because that is a range. Okay, so index equal to 0 is the easiest one, right? We just need to go, because if I am larger than this, if I am smaller, okay, so for L in lefts, because we'll have to go through every single one, and then if L is smaller than right, so if the current left is smaller than my right, then we need to compare the interval, right? Now we say if interval, self.interval, that's just the right, is smaller than right. In that case, my left and right covers the entirety of this current interval. Then we just say self.count minus equal to self.intervals left minus left plus 1. So we can completely remove this entire thing. And we can say self.intervals.pop L. we can pop it as well, because it doesn't exist anymore. And then we can move on to the next one. So elif self dot intervals L is equal to right. What if they're equal? Well, if they're equal, then we still cover. So we still do this, but yeah, we still do this. Because if the right is covering, then therefore this should be smaller equal to right. That's we cover it. Else, if the interval L, which means the right, is larger than my current right, and my left is actually smaller than your right, than your left. So if that's the case, then we have an overlap, right? So in that case, what we can do is to merge these two, okay? We need to merge these two. How do we merge these two? Well, we merge these two by, I don't want to pop, so I don't think it's necessary. I just need to change. Hold on. Okay. And why is this so complicated? I'll wash the dishes. So, okay, so the large condition is L is smaller than right. So the left is smaller than right. And what I find now is if the right, if the interval is smaller, you go to right. We can pop it out and take its impact. Now, if we have a new thing, all right, if the new thing, the L is still smaller than right, but the right is bigger than. So we have finally met our challenge. So now what do? Is we will change its left.
I took this from the box?
No, this is the letter.
Oh.
And we have to change the left interval. Okay. But we can't change, so we have to pop it as well. So we can pop that, right, to Yeah, we can pop it. And we change the right. So we're gonna do self.count minus equal to self.intervals L. So we're gonna say new right, because we're gonna pop it in. So new right shall equal to self.intervals pop. And count will be new right minus L plus 1, because we pop this one out. But we're gonna say right equals new right. And when this happens, we're gonna break. Okay, so this is when L is smaller than right. Right, so the L is smaller than right. Then we have to go through all this. Now, what if L is bigger? What if L is equal to right? If L is equal to right, then if L is equal to right, then intervals L. The intervals L can be smaller or equal to, which we can pop it. Yes. Then, or it can be like this. Then it will definitely be larger than right. And then new right equals to this, so we can pop this. Yes, so we can actually do smaller equal to. That'll be the same. But else is left, the new left is larger than right. And that's it. That's it. Right? That's it. We have found, we have encountered, we don't need to keep going. So that's break. So when we break, we have a left and right. And that's something we're going to insert it. We can say self.intervals left equals right and self.count plus equal to right minus left plus 1. So that's if index is equal to 0. Else, index is not equal to 0. If it's not equal to 0, that means it points to this one, right? That's the left. So what we're now going to do is left could be in between, right? Could be like here. Now, am I overlap with index minus 1 or am I not? Okay, so the easier condition is it's not overlapping with that, which is just to say if or left's index minus 1, that's the left, and now we say self.intervals, this is the right. Okay, so this is the right. If this right is smaller than the left, so which means left is in between 2, and so the previous one's right is smaller than the left. So in all this case, we shall start. So for I in range index towards line lefts, we can say L equals lefts I, because the left is larger than the previous left's right, so I can insert it directly. Okay, I can insert it the left directly, and then we just need to go from the index left, move on. All right, from the index left, and then this left would definitely be larger than left. So it's not larger equal to, but larger than. So that's that. So else will be self-dot intervals left is larger or equal to left. So we are overlapping. Okay? So we're overlapping. In this case, what do we do? Now we are overlapping. So now it seems to me, right? It seems to me what we need to handle, so the rest is always the same. All we need to handle is if index and self-dot intervals left's index -1 is larger or equal to left. This is what I want to handle. And after I handle this, the rest is the same. Right? After I handle this, this is the same thing. So I just need to handle this situation, which means the left extend the right more than the current left. So we need to basically restructure my left, right? We restructure my left. Basically, we're gonna pop that one out and then reset my left. Because the left doesn't really matter. As we go on, it's always on the right. So if that happens, I don't even care. If that happens, I basically just said left shall equal to left's index -1 and self.count minus equal to so previous left shall equal to this. This is the previous left, right? And then this shall equal to self.intervals pop. I'm already popping it. Pre-left minus pre-left plus 1. So we delete that, and then we say left is equal to pre-left. We just, because they overlap, right? These two overlap. So I pop up whatever we have, and then the current left extending here. And then we're just going to go from my index, right? So it's index is 0, or index is not 0. Whatever the index is, from this index going on, for each L, we're going to compare to the right. And then we're going to blah, 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 do all this, and basically popping them out. And then at the end, we add the left and the right, and then we do this. So I think that is it. So that's my add. Let's see if it works. Well, we have 2 intervals, so let me comment out this thing. Yeah, let's, before comment out. This works, but TLE, when there are a lot of non-overlapping intervals over a huge range. Yeah, that's the downside of this method. So I'm just going to comment it out and run this. Int object is not countable. Huh? What? Count intervals. How is that int object? What the hell did I do? What? Oh, I see. We have the two things are the same. All right, so we have to change that to current count. All right, that's okay. That is okay. All right, it's not right, but a good part of this is we can expect print self.intervals self.current count. All right. So I have 36. And now we have 9. What the heck? It's supposed to be the covering. Huh? So I have 8, right? 8 and a 43. So the next one is 13, 16 coming in. So 13 comes in. The right, no. So left is just 8. Bisect 13, so index is outside. So if index and minus 1 is larger or equal to, which is 8 is larger or equal to no, therefore we're going to go from index towards the end, which supposedly this is just 1 to 1, so we shouldn't even do this. No. If index and then minus 1 is larger than, this is true, larger than the left, this is true, then pre-left is equal to this. Oh, I see. So if the previous left, we have to still compare the right. Madre mia. It's the previous one's right. Right is previous left. The right is larger than the current. And we need to compare. Okay? We need to compare. It only works, right? It only works if, so it's like this situation, right? So if this situation depends on my right, yes, it depends on my right. But no matter what, this is doable. But whether we pop, that's a different problem. That's a different question, right? That's a different question. So we need to say if self.intervals pre-left, so which is the right, is larger or equal to the current right, then we would just return, right? We just return. It's like completely covering. So completely covered. So the current is completely covered. So current interval completely covered. Current interval completely covered by previous interval. Right? Because the right is larger than the current right. And it's left. And it's -1 to the left. So it's just completely covered. So don't do anything. Else, it's sticking out. So it's smaller than the current right. And the smaller, then we're gonna pop original, right? And my left into this left. Right is the current right. Then we're gonna go through. So let's try this thing. It didn't count again, but it is actually correct. Right? It's actually correct. So what is my print statement? Okay. New solution. Put it in. And we have all these test cases. Looks pretty good. Run it. Wrong answer. Oh, that's a huge one. Oh, gotta be something I did not pay attention to. Got too big. $977. Where is $977? Here, 977. I got it 1200. That's odd because the maximum right now is 994. I don't see a larger interval. So that's really strange. How do we debug this? I don't know. Let's do self-taught intervals. How many times do we add? Because I returned. That's the only time that we changed. So 906, right? Now we can see 906, they're all correct. So all the 906 is correct. Actually, 966 probably is correct as well. So we have 925. So 20 to 925. 20 is here, so 20, 925. And this one is in between. This one's in between, this one's in between, this one's in between. And then we have, and then we have 15 to 335. These two overlapped. 335. How do we get a 15? Where did 15 comes from? Hold up. That is 15. But 994 comes first. We got 20, 925. So 20 to 925. I supposed to see it increase. No, I supposed to see a 935 to 944. What happened to 935 and 944? Oh, actually, this one's not. I don't see 935. Oh, I see. I need to put one here. And then you see. I have 972. So 972. Okay, this shall be counted together. But technically, they don't overlap, right? So 994. And then this is covered. And then we have a 15. So we have 1000. Uh, 972. And then 15 to 335 is supposed to be a equal to 0 situation. Why did I add it to this? Well, to know, self dot min left max right. That is not correct. That is so wrong on so many levels. If right is smaller than min left, then min left equal to left. Yeah. And then, how is that 365? Aleph. No, it's fine. If right is smaller than left, min left. It's here. I didn't update here. So say self dot min left equals min, self dot min left left, self dot max right equals max, max right right. Yep, this is how it's supposed to go. Now we don't have an issue. Yeah, it's just the update. My bad. Can you take a little bit more? Yep. Okay, let's try this. All right. Finally. Oh my god. Starting from the 9, 10, 11, 12, 13, 5 days. Well, granted, I think 2 days. 2 of those days I didn't really take a look at this. But oh my god, 5 days to do this. This is, how should I say it? I stayed away from this method at the beginning. Actually, no, you did not think about this method. You're thinking about the intervals. And you were like, okay, I'm going to have to pop things out. How am I going to do this? So the use of the inspiration comes from here. This post. We use a dictionary to keep track of all current non-overlapping intervals. Then for each new interval, we sort, and the dict key is Alright, let's finish it up. The dict key is the left. And the value, the right interval. Each time a new interval is added, we sort the keys and binary search to locate where the new left can be. Then we iterate through all the lefts bigger than the current one and see how many intervals can be popped. Eventually, we add the newly merged interval and update the total count along the way. Yeah, that's how it is. Will be O1 login per add call, O1 per count call. Okay, finally. God, what a tough one. I mean, it's not really tough. I mean, it's just analysis, right? All this code is just analysis. But the idea is quite... Yeah, I still like this, honestly. I still like the segment tree, but it just didn't work. And I don't want to read why it will work. I just leave it. Too many days have been spent on this. Alright, I'll be there. I'll end here right now, and I'll see you guys tomorrow. Adios.